Hello everyone, I'm Jonathan and I'm thrilled to share with you my FYP project, Understanding Adversarial Attacks on Autonomous Vehicles Perception Modules. This is my presentation outline. I will first share some background and motivation, then talk about whether multiple cameras with overlapping field of view is sufficient as an adversarial defense. I will also talk about feature squeezing as countermeasures, including the experiments which I've done. We will also look at automating attacks using tools with a larger dataset, and then discuss some of the possible future works. First, background and motivation. The technological breakthroughs in autonomous vehicles are largely achieved mainly with the help of machine learning, specifically deep neural networks, which contributes to almost every modules of autonomous vehicles, such as perception, localization, planning, and prediction. Perception is a fundamental element of autonomous vehicles, involving in most decisions made by other modules. Sensors such as cameras and lidars gather information about the surrounding environment, such as traffic signs and pedestrians. As such, any error arising from the perception module can lead to wrong decisions from other modules, which can result in catastrophic outcomes. In Singapore, autonomous vehicles are under the Smart Nation initiatives, and many companies and universities, including A-Star, Nanyang Technological University, and National University of Singapore, have AV trials on the road to study the potential of autonomous vehicles. As such, autonomous vehicles have a foreseeable future to be a huge part of our roads in the near future. The origin of adversarial attacks on machine learning models can be traced back to a research paper published in 2013 by Ian Goodfellow and his team. Their work titled Explaining and Harnessing Adversarial Examples introduced the notion of adversarial examples. These are input data that can intentionally mislead a machine learning model. Following this work, adversarial attacks have gained significant attention and found applications in various domains, including autonomous vehicles. One of the most famous examples of an adversarial image shown below is taken from the aforementioned paper. Here, starting with the image of a panda, the attacker adds small perturbations to the original image, which results in the model labeling this image as a given, with high confidence. In fact, there are many other forms of attacks which are possible on autonomous vehicles. It is important to note that this list is non-exhaustive, and attackers are constantly developing new techniques to target autonomous vehicles. Next, we will talk about multiple cameras with overlapping field of view. The goal of an adversarial attack is to create an object that is invisible to the perception model, as shown in the figure below. To improve robustness for this attack, researchers have applied expectations over transformation on the optimization problem, and thus changing the optimization equation. The table below shows that using multiple cameras with overlapping field of view is more robust than relying on just one camera. We can see that the attack success rate falls from 78 to 43.75%. However, the attack success rate is still relatively high. Therefore, we discussed 3 additional countermeasures in addition to the demonstration of using multiple cameras with overlapping field of views. This figure illustrates the multiple protection techniques which the autonomous vehicle possesses in an ideal situation. On the hardware implementation side, the multiple camera setup capture visual data from various angles and feed it to the vehicle CPU, allowing the vehicle to be aware of its surroundings. The LiDAR sensor emits laser pulses and measures the time it takes for the pulses to bounce back, allowing it to create a detailed 3D map of the vehicle's environment. On the software squeezing side, feature squeezing involves reducing the amount of information in the input data fed into the vehicle's neural network, of which image compression, median smoothing, and color depth reduction will be discussed below. Adversarial training of the neural network can help you to gain exposure to a variety of simulated attacks, which can help to make the network more resilient in the face of real-world attacks. All these techniques provide the autonomous vehicle with the protection it requires for a safety ride. Feature squeezing is a technique that can help to mitigate adversarial attacks on machine learning models by restricting the amount of information available to attackers. By decreasing the number of dimensions in the input space, this method can make it challenging for attackers to add perturbations that cause the model to misclassify inputs. For instance, in a 2-dimensional input space, attackers can add perturbations along either dimensions to fool the model. However, If the input space is reduced to one dimension, attackers only have one axis to exploit, making it more difficult for them to find effective perturbations. Moreover, feature squeezing can reduce the impact of noise in the input by applying non-linear transformations that smooth out the input's noise. This smoothing effect diminishes the noise's impact on the model's prediction, making it more challenging for attackers to create inputs that the models will misclassify. Overall, feature squeezing is a valuable technique for enhancing model robustness against adversarial attacks by reducing the amount of information that is available to attackers and mitigating the impact of noise in the input. Also recently, it has been reported that explainable AI has been applied in several critical domain applications, including autonomous driving. We can see that neural networks perform the best, but at the same time have the poorest interpretability. Understanding how neural networks make decisions and what factors contribute to their vulnerability to attacks can be challenging due to their complex nature, involving many layers and millions of parameters. This lack of interpretability makes it difficult to develop effective defenses against adversarial attacks, as it may be unclear which aspect of the network's architecture or training data are contributing to its vulnerability. To address this challenge, it is crucial to balance the performance of neural networks with their interpretability when developing strategies for adversarial attacks and defenses in autonomous vehicles. This could include developing new training and design approaches that prioritizes interpretability, as well as devising new techniques for real-time explanation of the decisions made by these networks. Next, we will talk about the experiments which were conducted. Before that, I would like to share with you the scenario and object datasets which we have utilized. Due to the lack of real-world physical resources, open-source sensor dataset from Agro AI's Algoverse 2 was used. It consists of 1,000 scenarios from 7 ring cameras, 2 stereo cameras, and 2 LiDAR cameras, and each camera have overlapping field of view with its neighboring cameras. For object dataset, symmetrical 3D benign objects with simple textures are used. Objects obtained from online sources are processed with Blender, an open-source 3D graphics software. Lastly, for perception models, Pi2 Apollo for LiDAR and YOLO V3 for cameras were used. Let's talk about the first technique, image compression. Image compression is a type of data compression that uses a few bits to encode the original image. The goal of image compression is to reduce the image redundancy and to store or transmit data in an efficient manner. This produces an image that is more difficult for an adversarial attack to exploit, while still preserving the information required for the machine learning model to make accurate predictions. As seen from the figures below, we can observe that the original image and the compressed image are virtually indistinguishable. From the results, it can be seen that image compression techniques were successful in reducing the threats significantly. The results have been compiled onto a table which displays various compression levels on its left-hand margin, along with corresponding numbers indicating the efficiency of detecting objects such as fire hydrants and cars. These outcomes vary depending upon specific categories within each class, namely, accuracy metrics demonstrating how well each object is detected without incorrect identification despite image distortions caused by adversaries' attempt at subversion through malicious means. At the highest level of compression, detection was successful for both fire hydrants and cars with a precision of 99.9%. This indicates that this advanced form of compressing proved highly efficient when dealing with adversarial attacks against these specific classes, reducing their impacts significantly. As the degree of compression dwindled, there was a proportional decline in the precision of detecting objects belonging to all categories. Nonetheless, even at level 16, detection ratios for both fire hydrants and cars remained high at 94.1 and 88.4 to 99.9% respectively. It should note that in real-life scenarios, the level of image compression will not be as low as 8. The consistency of results for image compression as a defense against adversarial attacks can be affected by a number of factors, including the type of scene and the specific image compression algorithm being used. Different types of scenes may have different levels of complexity and detail, which can affect the effectiveness of image compression algorithms. Therefore, 15 frames are selected, with different intervals in between, and experimented to evaluate whether the results for image compression are consistent across the different scenes. From the table, it can be observed that the compression performance is consistent across different frames for different object classes. For some frames, certain object classes are not present in the scene. This implies that the compression performance of an object class is dependent on its presence in the scene. This also explains the lower performance for some of the frames, whereby the object may be further away from the field of view, hence resulting in a lower score. Overall, the results support the claim of consistency of image compression, with various factors including the presence of object in the scene and the distance from the field of view. Next technique, median smoothing. Median smoothing is a technique for smoothing out details and reducing noise in an image. The filtering method can take advantage of the fact that the adversarial perturbation is mostly high-frequency noise whose intensity is used to filter out the high-frequency components, reducing the influence of adversarial perturbation. Even though it might affect the accuracy of the classification, it is still commonly used as a defense against adversarial attacks. As seen from the results, suitable amount of median smoothing can help to defend against adversarial attacks. However, after a threshold of 5, the image is too smooth for the model to detect the fire hydrant. Lastly, color depth reduction. Color quantization, which reduces color depth, is shown to affect the performance of convolutional neural networks. According to works done by researchers, a neural network perceives the input space as continuous due to its differentiable manner. Hence, the color distortions affect the way neural networks perceive the input. Therefore, color depth reduction can mitigate the effect of the adversarial examples. However, if the number of colors is drastically reduced, then the object detection performance also drops accordingly. Hence, a hybrid approach of combining both 24-bit and 8-bit image is adopted. This leads to a more robust result, with 99% benign detection rate and only 13% attack success rate. Now, we will look at the possibility of automating attacks using tools with larger dataset. With the advent of AI tools such as ChatGPT, and more specifically DALL-E in the case of our research, it is important that we further study on how such tools can be leveraged to create adversarial attacks easily. At this point in time, creating adversarial images require a certain level of skills and understanding, but such technologies enable even a common man to launch an adversarial attack without much technical skills. This is an important area to look into, as this would open up more possibilities for a larger number of attacks. This figure shows the image generated by DALL-E with the prompt, "Create an adversarial image that will fool an autonomous vehicle camera system." And this is using the prompt, "Create a stop sign adversarial image that will fool an autonomous vehicle's camera system." DALL-E is a particular instance of a two-part model made of a prior and a decoder. By concatenating both models, we can go from a sentence to an image. We input a sentence into the black box and it outputs a well-defined image. However, the generated images are based on the pre-trained dataset, and hence, any prompts which are outside of its pre-trained models may lead to inaccurate outputs, which is the case in the figures shown in the previous two slides. Lastly, future works. By looking at other potential adversarial attacks, we can gain insights into the characteristics and properties of other forms of adversarial inputs and the limitations of existing defensive mechanisms. This information can be used to improve the design of neural networks and other components of autonomous vehicle systems, to develop more effective detection and defense mechanisms, and to identify areas for future research. Spatially transformed attacks manipulates the spatial arrangement of an image in order to fool the machine learning model. To perform a spatially transformed adversarial attack, the attacker will require a reference image and a target class for the attack. The attacker will then apply various transformations to the image in order to create a modified image that is similar to the original but has a different spatial arrangement. Next, one-pixel attack. One-pixel attack is a type of adversarial attack which involves making small targeted changes to an image that are undetectable with human eyes, but can cause a misclassification in the machine learning model. One-pixel attack usually involves changing only a single pixel in the image, although more complex variants of the attack can involve changing multiple pixels. To perform a one-pixel attack, the attacker will typically start with a reference image and a target class for the attack. The attacker will then make small targeted changes to the image, such as changing the color or intensity of a single pixel, in order to create a modified image that is similar to the original but has a different appearance. The attacker will then feed the modified image to the machine learning model and check whether the model predicts the target class. If the model predicts the target class, the attack has been successful and a modified image is an adversarial example. However, There are a number of approaches that can be used to improve the robustness of machine learning models against these attacks. For example, models can be trained on data that has been augmented with one-pixel attacks, which can help the model to learn and identify and reject these types of perturbations. Lastly, zeroth order optimization-based attack. This attack requires an effective black box attack that only requires access to the image and the confidence score of a targeted DNN. The attack is formularized as an optimization problem and proposes a new loss function suitable for the black box setting. Zeroth order stochastic coordinate descent is used to optimize on the target DNN directly, along with dimension reduction, hierarchical attacks, and important sampling techniques to make the attack efficient. With that, I hope there is a better understanding on autonomous vehicles and its associated adversarial attacks and defenses. Thank you.